Welcome to the sixth and final video in our series. Today, we bring everything together in one of the most powerful applications of mathematics, modeling with differential equations. We will see how these equations shape our world. Why do we spend so much time solving differential equations? Because they perfectly describe real-world rates of change. Whether you are tracking the heat escaping from a cooling cup of coffee, or predicting the growth of a biological population, differential equations provide the mathematical framework. Let us start with Newton's law of cooling. It states that the rate of temperature change of an object is directly proportional to the difference between its own temperature and the ambient temperature of its surroundings. The larger the gap, the faster the cooling. Solving this first-order linear differential equation using separation of variables yields an exponential decay function. For example, if you place hot coffee in a 25-degree room, integration gives us a specific temperature function that perfectly predicts how the heat dissipates over time. Plotting this solution makes the behavior crystal clear. The temperature drops dramatically at first when the coffee is piping hot, but as it gradually approaches the ambient room temperature, the tangent lines flatten out. The slope approaches zero as it reaches thermal equilibrium. Now, let us switch gears to population growth. Unrestricted populations grow exponentially, doubling at a constant rate. However, real-world environments have limited space and food. This introduces a natural ceiling on growth, known as the carrying capacity of the ecosystem. To account for limited resources, we use the logistic differential equation. It starts with an exponential growth term, but multiplies it by a restraining factor. As the population approaches the carrying capacity k, this factor approaches zero, hitting the brakes on the growth rate. Solving this yields the famous logistic S-curve. The population accelerates early on when resources are plentiful. But after reaching an inflection point, the growth slows down, and the population asymptotically approaches the carrying capacity limit, without ever crossing it. This is the profound power of calculus. Model the instantaneous rate of change, solve the underlying differential equation, and you can literally predict the future of a system. Thank you for watching.